Module 6, Investigation 3, Graphing Rational Functions and Understanding Limits. Use these four rational functions, 1 through 4, to answer the questions 1 through 7. See, first remember that a rational function is just one polynomial divided by another. We have polynomials in the numerator and denominators of all these functions. Notice that this is a linear polynomial. Here's a quadratic polynomial. Let's see, the first thing we're asked to do is to find the real zeros or roots of each function. You could do this all sorts of ways. You could graph it on your calculator and calculate the zeros. But I'm just going to note here that for each of these rational functions, the only way that we're going to get 0 for our output is if the numerator is 0. For every one of these, I know that I'm going to have zeros when my numerator is equal to 0. Because if I plug in 3 to this function, 3 minus 3 is 0, divided by 2 is equal to 0. That's basically my check, so that you can see that I have indeed found the 0 or the root. I have 0 over 5, which is 0. Let's see, so for this one, I can just set that numerator equal to 0, divide by 3, so x squared is 0. The only way that this happens is if x equals 0. So there's my root. I could check it by plugging 0 into my function, and again we'll get 0. Let's try h of x. All we got to do is set x squared plus 1 equal to 0, but this will never equal 0 because we're taking a square, we're adding 1. That will always be 1 or greater, because the squares can never be negative. Here 5x equals 0, that means x equals 0. There is my root. Determine the vertical intercept of each function. Okay, vertical intercept. That means what we usually call the y-intercept. But that is when x is 0. So to find it, all we need to do is plug 0 in for x. And we get negative 3/2. So you could say negative 3/2 is your answer if you wrote this as an ordered pair, 0, negative 3/2. That's a little bit more appropriate because it is the vertical intercept is a point, but either one of these is acceptable for grading purposes. So we just need to find out what is the value of y when x is 0, because if we cross the y-axis, x is 0. So here this one would be 0 over negative 1, negative 3, which is 0. So the point 0, 0 is my vertical intercept. Here h of 0, that would be 0 squared plus 1 over 0 minus 2, negative 1/2. There's my vertical intercept. I could write it as the point 0, negative 1/2. For k of 0 is 5 times 0 over 0 squared minus 4, which is 0. 0, 0. You may notice that in all of these places where the real 0 or the x-intercept was 0, the vertical intercept was also 0. So that's going to be a pretty consistent pattern as you move on into pre-calculus and calculus. Describe your method for determining the vertical intercept of each function and explain why this method works. So we find the vertical intercept by evaluating each function at x equals 0. And this works because the graph of a function crosses the vertical axis whenever x equals 0. So what is the domain of each function? So the definition that we're working with, the domain is all possible inputs. And remember that we can't divide by 0, so here -2 is not an input. Here 1 and 3 are not inputs. In function h, 2 is not a possible input. And in function k, neither 2 or -2 are possible inputs. So for first function, we could say the domain is all real numbers except 2. For the next one, we have all real numbers except 1 or 3. Then all real numbers except 2. And all real numbers except 2 or -2. So what happens at the values you excluded from your domain in part A? So all these places where we're dividing by 0, hopefully we've learned that there are vertical asymptotes at each of those points. So clearly this makes no sense at all. Using what you learned in worksheet 2, fill in the blanks below. I don't have any blanks here. Hopefully you have something. Yeah, I'm just going to look at the answer key that I have and hope that this makes sense. So as x goes to infinity, what happens to f of x? Let's look at our function. Here, notice that the numerator is a linear function and the denominator is the linear function also. So there's not going to be much of a difference between the numerator and denominator. Their values are going to be pretty close as x goes to infinity. Both of them have a degree of 1, and both have a leading coefficient of 1. Whenever your degrees of the numerator and denominator are equal, the limit as x goes to infinity is the ratio of the leading coefficients, 1 over 1. So this will be 1 over 1, which is 1. Let's see, now as x goes to negative infinity, it'll still be 1. Our f of x will still go to 1 because we'll have a negative over a negative. Give us a positive 1. And that means that we have a horizontal asymptote. Horizontal asymptote at y equals 1, and I totally spelled that wrong. Okay, so the next few are similar. We're just looking really for the horizontal asymptotes. As x goes to infinity, what happens to this function? If you multiply all this out, you'll have x squared, and really that's all that matters here. The degrees are the same, so the limit is the ratio of the leading coefficients, 3 over 1. And what is this function? It is g of x. G of x goes to 3 over 1, which is 3. And then you could use your calculator and note that as x goes to negative infinity, g of x also just goes to 3. And so we have a horizontal asymptote at y equals 3. So for number 3, what happens as x goes to infinity? Let's see, our function is x squared plus 1 over x minus 2. Notice that the numerator is a quadratic and the denominator is linear. The numerator will grow much faster than the denominator. So that ratio of the numerator over denominator will get bigger and bigger and bigger, and the whole function will go to infinity. H of x goes to infinity, and as x goes to negative infinity, let's see, the numerator will be positive and the denominator will be negative. So we're going to go to negative infinity in that case. Now if you go to infinity in both directions, there's no horizontal asymptote. So what happens with the last function? We have a linear function on top and a quadratic on bottom. The quadratic will get larger much quicker than the linear function will, so this ratio will approach 0. So as x goes to infinity, k of x goes to 0. As x goes to negative infinity, it will be 0. That means we have a horizontal asymptote at y equals 0. Combine the information from your answers above to sketch a graph of each function. Once you have sketched your graphs, use a calculator to graph the function and compare. If your sketch was incorrect, write a brief description of your error and why it was incorrect. Remember that if you ever get stuck regarding how a function behaves on a given interval, you can always create a table of values. So let's look at f of x, x minus 3 over x plus 2. We could simply create a table of values, plug in lots of x values, see what the corresponding y values, and plot those and connect the dots. But we have lots of neat information that will help us to graph this one fairly easily. First, our 0, where we cross the x-axis, our root is 3. So I know that this is again the graph of f of x. At 1, 2, 3, my function will cross the x-axis. There's the root, x-intercept, or 0. Now I also know that the vertical intercept is negative 3/2. So that means, let's see, at negative 3/2, that's negative 1.5. I'm going to have my function there. What else? We have the domain, all real numbers except 2, and what happens at the values you excluded from your domain? There are vertical asymptotes there. So in ours at x equals 2, we're going to have a vertical asymptote. This really should be right on the line. So that red dashed line is my vertical asymptote. We also said that we had a horizontal asymptote at y equals 1. So at y equals 1, we have a horizontal asymptote. Now, believe it or not, this is all that we need to graph our function. We know that as x goes to infinity, the graph, or the output, approaches 1. So we're going to approach that horizontal asymptote, but we're never going to reach it. We have a vertical asymptote here. And so our function is going to just approach this vertical asymptote, but never quite reach it. And then we're going to have the same general pattern here. And you'll get a much prettier graph, I hope, that I'm able to get on this computer screen. Let's think about graphing G. We know that the x-intercept is 0. So we're going to cross our function's going across the x-axis at the origin. The vertical intercept is 0. That's at the same spot. Okay, I had some really bad technical difficulties mathematically graphing this thing, so try this again. Here's the origin, and we know that that's our function's going to cross the origin. We also have vertical asymptotes at 1 and 3. We have a horizontal asymptote at y equals 3. Okay, now that's all we got. Got this point here. We know as x goes to negative infinity, we go to 3. That's our horizontal asymptote. So the graph is going to look like this. Then we have that vertical asymptote here as we approach 3, something like that. Looking at a table of values, I see that if I'm in the middle here, then all my values are negative, and we make a shape like this. And then over here, if I just choose a value like 4, for instance, g of 4 would be, you could again look at this on your calculator, 4 minus 1, 4 minus 3. I think that would turn out to be 16. So it's way up here, so the function comes down like this, approaching those asymptotes. And your graphing calculator will give you a better one than this one. So I've already started on this one. X squared plus 1 over x minus 2. We have a vertical asymptote at 2. And that's pretty much all we got. I think we also had the intercept was negative 1/2. So with this one, this is pretty tedious, but if you keep plotting points, you're going to get a graph like this. Right down the middle we have what's called a slant asymptote. If you used long division, polynomial long division, you could find the equation of that asymptote. This lesson is so frustrating, I had to get a beer. Maybe this function won't be so bad to graph. Let's see. Let me get better color. Green. That one looks cool. So, intercepts are at the origin. Asymptotes at 2 and negative 2. Horizontal asymptote at 0. I think we got this. Let me just keep track of this one. Okay, so now the functions here, we can clearly see that I have lost my pen. Here it is. Intercept is 0. We have vertical asymptotes at negative 2 and 2. that's everything that we've got. Oh yeah, and we have a horizontal asymptote at y equals 0, but we don't have enough information to solve this one. Okay, as I was saying, let's look at k of 1. 5 times 1, 1 squared minus 4, 5 over negative 3. So about right here. If we use negative 1, it's negative 5 over negative 3, positive 5/3. Right here. Right here. Okay. This is enough information for me to be pretty sure the graph will look like this. Okay, so now we can plot some other points above 2 and below negative 2, and you'll find the graph looks something like this. That's not very good. Remember that horizontal asymptote at y equals 0. Okay, sketch a graph. Let's take a look at this one. Notice that there is a vertical asymptote at x equals 5. So I'm going to go ahead and come to my graph where x equals 5. I can put a vertical asymptote. Okay. Next, I know there's a horizontal asymptote at y equals 1 because the leading coefficients, the ratio is 1 over 1. These are both linear functions, have the same degree. So y equals 1. Okay, what else do we know? We know if we plug 0 into the function, we'll get, what will we get? 7 over negative 5. That's the y-intercept. So that was negative 7 over 5. So our function is going to look something like this. Definitely should have gone through that y-intercept. Let's see, and I'm gonna just plot some more values, like if we plot g of 6 is 13 over 1, 13. So 1, 2, 3, 4, 5, 6, we're at way up here at 13, so that tells me we're going to have something that looks like that. With these other ones, I think maybe I'll do some sort of sketch, but I'm not going to be too precise. You know, something like this. You have a vertical asymptote at negative 4, and then you have a slant asymptote as well. And part C, let's see, this one goes up here. This one comes down here. Okay. I am not going to make you guys do these problems. Those aren't very fun. Limit notation is a concise way to communicate behavior about a function. For example, consider the function f of x equals x minus 3 over x plus 2. We say that the limit of a function is the value, or positive and negative infinity, that the outputs of a function approach as the input approaches a specified value, or increases or decreases without bound. For example, we know that f has a horizontal asymptote at y equals 1, so as x goes to infinity, f of x goes to 1. Therefore, we say the limit of f of x is 1 as x goes to infinity. And we write it as limit as x goes to infinity of f of x equals 1. Similarly, since f of x goes to 1 as x approaches negative infinity, we say the limit as x goes to negative infinity of f of x equals 1. We also know there is a vertical asymptote at x equals negative 2, and by plugging in a few values or looking at the graph, we can determine that f of x goes to negative infinity as x goes to negative 2 from the left. Therefore, we can condense f of x approaches negative infinity as x approaches negative 2 from the left using limit notation by writing limit as x goes to negative 2 from the left of f of x equals negative infinity. Similarly, f of x goes to infinity as x goes to negative 2 from the right, so the limit as x goes to negative 2 of f of x equals infinity. Use the following functions to answer the questions below. Note, if a value does not exist, write does not exist. Okay, this is going to be fun. 1, 1. I probably should tell you how I got those. So the degrees of the numerator and denominator are the same, so the limit as we go to infinity is the ratio of the leading coefficients. If we go to negative infinity, you have to think a little bit more, but each one will be negative, we'll divide, we'll get a positive 1. As we go from 6, we have a vertical asymptote, so these will either be positive or negative infinity. Think about if we go to 6 from the left, or negative 6, like we'll have negative 7. Just try negative 7. Negative 7 plus 3 is negative 4 over negative 1 is positive 4. So as we approach 6 from the left, we're positive. We're going up towards positive infinity. I know that because there's a vertical asymptote there. As we approach negative 6 from the right, like positive 7, we'll see negative 5. Negative 5 plus 3 is negative 2. Negative 5 plus 1 is positive 1. That's negative 2. We're going to go to negative infinity here. This one, it might help to simplify this, or not really simplify, just rewrite it as x squared minus 4x plus 3, which shows me that the limit as x goes to infinity is 3 over 1, just 3, because the ratio of the leading coefficients, because we have the same degree. As we approach 1 from the left, we're going to have an asymptote. So we're going to go to either positive or negative infinity. Think if you're coming from the left, you might be at, say, 0. If we plug in, well, that's not very useful. The way I used to do this when I was in calculus, I just graphed it. And then I saw what happened. As we approached 1 from the left, we go to infinity. As we approach 1 from the right, we go to negative infinity. And as we approach 3 from the right, we go to infinity. Check your graph. Here, as x goes to infinity, there's no horizontal asymptotes. This function is also going to go to infinity. As we approach negative infinity, because the numerator will be positive, the denominator will be negative, we'll go to negative infinity. As we go to 2 from the left, go ahead and graph this function. You'll see we have a vertical asymptote there. And as we approach 2 from the left we have negative infinity. 2 from the right we have positive infinity. This one, as x goes to infinity, we have 0 because the degree of the numerator is less than the degree of the denominator. We have a horizontal asymptote at 2 and negative 2. From the left, as we approach, that's negative 2. You can take a look on your graphing calculator and see that's negative infinity. Then as we approach positive 2 from the left, it's also negative infinity, and 2 from the right is positive infinity. In each part below, you are given information about a rational function. Use the information to sketch a possible graph of the function. So 7, limit as x goes to infinity of f of x equals negative 3. That means that at negative 3 we have a horizontal asymptote. As we go to 2 from the left to right, we get infinity and negative infinity, so we have a vertical asymptote at 2. So it just wants a possible graph. It doesn't have to be perfect. So as we approach infinity, we get to negative 3. As we approach 2 from the left, we go to infinity. So I'm thinking maybe something like this. And let's see, the other side, as we approach infinity, we get to negative 3, and as we approach 2 from the right, we get negative infinity, so probably something like this would work. And I'm just going to copy this. They say does not exist. That means we just go to infinity. Then that looks like negative 4 from the left, so I have an asymptote there. It's pretty much all we got. Let's see, as we approach it from the left, we're going down to negative infinity. So it could be anything. It could be something like this. Yeah, that's something it could be. Let's see, last one. Okay, we have horizontal asymptotes at 2. Just one horizontal asymptote at 2. At negative 3 we have a vertical asymptote. And at 1 we have a vertical asymptote. Notice as we approach 3 from the right we go to negative infinity, so I know that my graph has to go down like so. As we approach 3 from the left, we go to infinity, And as we approach 1, that's negative infinity. Hold on a second. This is negative 3. As we approach negative 3 from the left, we go to infinity. So probably something like this. As we approach negative 3 from the right, we go to negative infinity. Go down here, but we also have to think what happens as we approach 1 from the left, we go to negative infinity, so maybe something like this on both sides. And finally, as we go to 1 from the right, we go to infinity, so we need something like that. Sorry, this lecture was not any fun.